our journey begins a long time ago. We're going to talk about functions for just a second. Yeah. The first function here, I've got two, right? I have this one, and I have this one. Can you guys name this one, like the actual parent graph to that one? Parabola. Okay, what's the equation? X squared. Very good. What would this one be? The backwards S graph. And what's the actual function? X cubed. Okay, on to the next question. Does the graph represent a function? Let's go to this one first. Give me a thumbs up if it does. Thumbs down if it does not. Thumbs sideways if you have no idea. Go.
What was the question?
The first one. Does it represent a function? Thumbs up, thumbs down, thumbs sideways. Everyone's looking around. Oh, she's hiding closer. Okay, good. I see some up and I see some sideways. There's a very fast, easy way to tell if a graph represents a function. What is it? The vertical line test. Does this pass the vertical line test? Yes, it sure does, right? Take your pencil moving across. It does. So function, thumbs up, thumbs down. Still don't know. Show me real quick. There we go. Everyone's like, thumbs up. Good. Let's go to this one. Is this represent a function? X cubed. Function. Thumbs up, thumbs down, thumbs sideways. There you go. There you go. Yes, this does represent a function. How come?
Passes the vertical line test.
It passes the vertical line test. Okay, second question. Back over here to the parabola. Is it, and does this function have an inverse?
No.
Thumbs up, thumbs down, thumbs sideways. I see a thumbs up. I see thumbs up. Up, sideways. I see, I don't know what that is. Sideways, sideways, down. Okay, how can you tell by looking at a graph if it has an inverse? It has to pass the what? Horizontal line test. Does this pass the horizontal line test? No. So does it have an inverse? No, absolutely not. How about this one? Does this one have an inverse? Yes. Why? Okay, so both are functions, agreed?
Yeah.
But only one of them has an inverse, and we use the horizontal line test to tell right away. This is where our story begins, okay? Okay, and our journey takes us now into trig functions, okay? So, what I'd like you to do is I'd like you to draw a sine curve on the scale, on the domain from negative pi to positive pi, and it should look something like this when you're all done. So at negative pi, we can put a dot here, at negative pi over 2, here, there. So here's the next question I'm going to ask, right? So taking that, what we just talked about, functions and inverses for x squared and x cubed, does the sine curve represent a function? Yes or no? Yes, it does. Why? Because it passes the vertical line test. Okay, does the sine curve then have an inverse? No. So we have a problem. How can we even talk about the inverse sine function when the sine doesn't have an inverse? It doesn't pass the horizontal line test, okay? So mathematicians sat around a long time ago and said, well, what are we going to do? Well, they said, well, let's just restrict our domain, and let's just, so that it does pass the horizontal line test. So here's what they do, okay? If we restrict our domain, the first thing we do is we're going to restrict the domain for sine of x in between these two values, negative pi over 2, less than or equal to sine inverse of x, less than or equal to pi over 2. Okay? Now all of a sudden we can talk about it if we restrict our domain. So the first thing you have to understand about inverse trig functions is that they are on a very specific domain for the fact that it doesn't pass the horizontal line test without it. Okay, so I'm going to highlight from negative pi over 2 all the way to pi over 2. You need that like sort of nice looking S thing. You guys see that part? Now, if I draw a box just around this part, and we look only inside that little specific window, that passes both horizontal and vertical. Therefore, we can talk about the inverse sine function. Do you guys see how we solved the problem? Okay, so there's the first step, okay? Second thing is, I want to tell you how to read this, okay? This is read the sine inverse of x, okay? We read that, the sine inverse of x. So when you see that, you say negative pi over 2 is less than or equal to the sine inverse of x, which is less than or equal to pi over 2. That's how you say it. Now let's talk about what it means, okay? Whenever you see this, this is what your brain thinks. It says this: the angle whose sine sine or cosine or tangent, whichever one we're dealing with, is x. All right? This part right here is going to get you through the entire section, understanding what the sine inverse of x is. So your brain says it's the angle whose sine is blah, 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 whatever it is that we're looking for. Okay? So box number 1, we understand that we have to restrict the domain, and by definition the domain is restricted between negative pi over 2 and positive pi over 2 for the sine curve, and we read it sine inverse of x, and we say the angle whose sine is x. Is there anybody on board so far? Yeah? Okay, good. Let's do it. That's what I was looking for. Okay, let's talk about the sine inverse of 1. And what we're going to do is we're going to find the exact value for the sine inverse of 1. So, your brain says this. The angle whose sine is 1. Okay? That's how you read this. That's the answer to the question. So when we say, what's the sine inverse of 1? We're really saying, what's the angle whose sine is 1? Okay, now you have to realize that the sine inverse is restricted between negative pi over 2 and a positive pi over 2. So, if I take my bite size, which I have over here in this version, okay, where is negative pi over 2? Where's negative pi over 2? The negative pi over 2 is down here, right? Where's positive pi over 2? Up here, right? So the sine, the inverse sine function lives right over here in quadrant number 1 and quadrant number 4. And that's good news because it's positive in quadrant 1 and it's negative in quadrant 4. So what I'm really looking for is where on the unit circle is the sine equal to 1? And that'll be my answer. Yeah. If you look right up here at the top, right? This represents, remember it's x comma y. Y goes with sine. So the sine is equal to 1 when the angle is equal to pi over 2. So the answer, so the sine inverse of 1 is equal to a positive pi over 2. And that's really all there is to it. So you have to understand what that stuff means. Is it pi over 2 or can it be 90 degrees? No, we keep it in radians. The angle in radians, whose angle is that? So let me show you how your calculator interprets the same thing, okay? It's going to look like this. Whenever you're dealing with trig functions, you've got to be in radian mode. So turn your calculator on and check the mode. Make sure you're in radian mode. And then hit second quit. Okay, we're going to ask the calculator, what is the sine inverse? So now we get to actually push second sine. That brings up sine inverse. That is not the same thing as 1 over sine, like, cosecant is. So we have sine inverse of 1. Okay, we're going to ask the calculator. Calculator gives us 1.5707. That is the decimal equivalent to pi divided by 2. There you go. So the inverse sine of 1 is pi over 2. I don't know. Good question. No. Nope. Sure won't. Because I don't think it puts a pi in there for that, Alright? Alright, so inverse sine functions. So the graph that we usually draw here is this is negative pi over 2. Here's pi over 2. And sine lives either here or here. Positive in the first quadrant, negative in the fourth quadrant. Because the definition says we restrict our domain from negative pi over 2 to positive pi over 2. Alright, what do you guys think? Alright, let's draw a cosine curve from 0 to 2 pi. Here's 2 pi, there's pi, pi over 2, 3 pi over 2, 1, negative 1. Okay, does cosine start at 0 or does cosine start at 1? Cosine starts at 1, yeah. So a dot there, a dot there, a dot there, a dot there, and a dot there. So here's my regular old cosine curve, right? And we run into the same problem, right? We run into the fact that, yes, this is a function, but no, this does not have an inverse because it does not pass the horizontal line test. So we restrict the domain again. The story remains the same. So we're going to restrict it 0 less than or equal to cosine inverse of x less than or equal to pi. This is by definition. So we restrict our domain only to this piece right here. And now all of a sudden, we can talk about an inverse cosine. So these are on very, very short restricted domains. All right, so let's examine one of these then. What would be the cosine inverse of root 2 over 2? Okay, the cosine inverse of root 2 over 2. Let's play with this one here. Well, I know cosine is restricted from 0 to pi, because that says so in my domain. I know this is pi over 2, so it's somewhere either in quadrant number 1 or quadrant number 2. In quadrant 1, cosines are positive. In quadrant 2, cosines are negative. So I know I must be looking at quadrant 1 because this is rad 2 over 2. So really the question is, where on the unit circle is the cosine a value of rad 2 over 2? Remember, that's the x value. What angle would that have to be? Pi over 4, exactly. So the inverse cosine of rad 2 over 2 is pi over 4. And we'll verify that on the calculator. We'll ask the calculator and we'll say, what is the inverse cosine of square root of 2 divided by 2? And it will give us this. That's not right. What do I have?
2 divided by 2 on the same thing.
Second entry. Oh, thanks a lot. Square root of 2, then divide 2. Thank you. And boom, there we go. Second pi divided by 4. Same exact answer. So inverse cosine of rad 2 over 2 is just pi over 4. So the inverse cosine lives between 0 and pi. All right, and then we'll do a tangent. Okay, tangent is a funky graph. So we're going to restrict our domain in between negative pi over 2 less than or equal to tan inverse of x less than or equal to positive pi over 2. Oh, excuse me. Definitely not less than or equal to. We'll talk about that. So, here's negative pi over 2. Here's positive pi over 2. Halfway between is pi over 4. Negative pi over 4. We have vertical asymptotes. Remember, at any multiple of pi over 2. And the tangent function looks like this. So because we have asymptotes here and here, we're not allowed to actually include them in our restricted domain. That's why it's just strictly less than. So again, our tangent then is the exact same picture that we draw for sine. So here's negative pi over 2, and here's a positive pi over 2, and it lives over here. Positive in quadrant 1, negative in quadrant 4. And I'll bring this down over here. Oh. Sorry. All right, so let's do this one. Let's find the inverse tangent of negative square root of 3. What's the inverse tangent of negative square root of 3? Let's evaluate that and find the exact value. So what is our brain saying for inverse tangent of negative square root of 3? What do we want? The angle? The angle whose tangent is negative rad 3. Okay, I don't need 2 of these out here, so delete that one. So the angle whose tangent is negative rad 3. So we're going to look on our bite size here. We're going to restrict our looking from the first quadrant and the fourth quadrant. Okay, and we want our angle is negative, so we must be down here in quadrant number 4. And what we're looking for is a tangent that is negative square root of 3. Remember, tangent is sine over cosine, so it's going to be the
60.
Yeah, it's going to be the second one divided by the first one, right? Okay, so is it this one? Is it 11 pi over 6? No, it's definitely not the middle one, so it must be this one, right? Okay, now, so is the answer 5 pi over 3? No. Why is the answer not 5 pi over 3?
Because that would be going around.
Yes, because that would be going outside of our illegal boundary, right? So instead, we need to swing down, and the answer would be what? Negative pi over 3. Beautiful job. Nicely interpreted. So, if I ask the calculator, say, calculator, what is the inverse tangent of negative square root of 3. The answer is going to be a negative answer. Look, negative something. And that's because it has to stay within those restricted bounds. So I can check that by saying, what's the negative pi divided by 3? And look, I get the exact same thing. All right? So really all this boils down to is drawing the right picture in the right quadrant and asking yourself that very basic question, the angle whose sine is or whose cosine is or whose tangent is, okay? All right, let's do number 11 in your homework right now. I'll start you off, okay? As an added bonus. Number 11 is the inverse cosine of negative root 3 over 2. Whoa. The inverse cosine of negative root 3 over 2. Okay, what does our brain say? What does my brain say? How does my brain interpret this? Everybody. Uh-oh, nobody. Uh-oh. The angle whose cosine is negative rad 3 over 2. Good. So we draw, it looks like this. Cosine lives between 0 and pi. Pi over 2. Right, we restrict it. So it's positive here and it's negative there. So which quadrant do we have to be in? We have to be in quadrant 2. And so we are looking for the spot on the unit circle where the cosine is negative rad 3 over 2. And what would that angle have to be? No, not 30 degrees. 30 degrees is in quadrant 1. 150, which would be 5 pi over 6. There you go. 5 pi over 6. So you want to keep our answer in radian, okay? So we can check to see if we did this right. We could ask the calculator for the inverse cosine of negative root 3 all divided by 2. And it spits out a positive 2 point blah, blah, blah. That's 5 pi divided by 6. Look, exactly the same thing. Okay? So tonight is an introduction. All of the problems are just like this one right here. All right? Feeling pretty good? All right, sweet. Nicely done. Grab yourself a book. Grab yourself a partner.